Okay, today we're going to look at some special right triangles. We're going to start off with looking at a square. And if I take a square and draw the diagonal, then what I'm going to get here, a square, remember, it has 4 right angles at 90 degrees. And when I draw a diagonal in a square, then the diagonal will bisect the opposite angles, which means that this angle is 45 degrees. And this angle is 45 degrees. So what this creates is a right triangle called a 45, 45, 90. And it's a special right triangle. Why is it special? Is because we're going to learn how to find their side relationships without having to go through Pythagorean theorem all the time, because there's a certain pattern that's associated with this. So to show you it, let's go through the Pythagorean theorem the first time. So Pythagorean theorem says that in a right triangle, that side squared plus side squared is the hypotenuse squared. And so let's take the side squared plus the side squared, and then we get some hypotenuse, which I'll use the letter C for. So we want to find out what C is. Add those up. That gives me 2 n squareds is C squared. And then I want to find C, so I'm going to take the square root of both sides. Now, normally when you take the square root of both sides, you need to put a plus or minus out in front. But because we're talking about lengths, the lengths cannot be negative, so we only need to worry about the positive version. So the square root of C squared is just C. And this is, it's 2 times the n squared. When I square root that, then I get basically n times the square root of 2. So in a 45, 45, 90 right triangle, each side is identical because it comes from a square. This is also called an isosceles right triangle. And the side length is the hypotenuse is going to be the same length, but times the square root of 2. So whatever the side length is, we just times it by the square root of 2, and I get the hypotenuse length. That's what makes us a special right triangle. So our side ratios are n to n to n times the square root of 2. And this allows me to find different values without having to do Pythagorean theorem all the time. I just need to memorize this ratio, and I have it as quick as I can. The other one over here is an equilateral triangle. And equilateral triangles means all the sides are the same length and all the angles are the same. So that means all these angles are 60 degrees because the angles of a triangle add up to be equal to 180. So in this particular case, I don't have a right triangle. So to create a right triangle, I need to draw the altitude or the height of this triangle. In doing so, I form a right triangle. In this right triangle, that is 90 degrees, that is 60 degrees, and this altitude will bisect this angle. So this angle up here is 30 degrees. So I end up with a 30, 60, 90 right triangle. Okay, here's my 60 degrees, here's my 30 degrees. So in this triangle, there are 3, see over here, these sides were the same length. Over here, they are different. This side that is opposite the 30 degrees is smaller than this side, which is opposite the 60 degrees. And the hypotenuse, obviously, is the largest side. So we want to find the same kind of ratios that this one had. So to do so, I'm going to put some values in here, just like I did over here. I'm going to call this n. So so in 30, 60, 90, the short side is the one you want to go to first. If you find that one, the other ones are easy to find. Now, how did this side length get created? Well, we divided this altitude, not only bisects this angle, but it also bisects the side. So if this side is n, then this is n. So the whole entire length is 2 times n. So that means this distance is half of the hypotenuse. Remember, it's equilateral, and so that's where that comes from. So the only thing that's left to do is to find this one over here. And again, we can use Pythagorean theorem to do so. I don't know the side length over here. I'll call it A for now. But I know from Pythagorean theorem that a squared plus n squared is 2n squared. So working this out, I got a squared plus n squared, and this is 4n squared. Moving that to the other side, a squared is now 3n squared. And then take the square root, and I get the length is n times the square root of 3. So this length over here will be the short length just times the square root of 3. So you can see that if I know the short length, I know the other two sides very quickly. Just know that I'm going to multiply this one by the square root of 3 and multiply that by 2 to give me the hypotenuse, which gives me the ratios that I want. N times the square root of 3, 2n. And that is the side ratios for a 30, 60, 90 triangle. So these are the things we wanted to use, and we're going to use these to help us find the side lengths, like I said. So let's look at some problems to see what we get. So looking at this one right here, the first one, this is a 45, 45, 90. I gave you the hypotenuse. What are the other two sides? Well, from our ratio, from the side length to the hypotenuse, I multiply by the square root of 2. So to go backwards from the hypotenuse back to the side, I obviously do the opposite, which is to divide by the square root of 2. So that means to go from here to here, m is 7 divided by the square root of 2. And since this is a 45, 45, 90, n is exactly the same thing. We want to have a simple radical form, which means we need to simplify this, which means you cannot have a square root in the bottom of a fraction. So you need to rationalize, which means I'm going to multiply the top and bottom by the square root of 2, because this product will eliminate the square root, and I end up with 7 times the square root of 2 divided by 2, which means this one is exactly the same thing. And so that's how I can use spectral right triangles to find side lengths of right triangles that are of these two types. Same thing over here. Identify the short side. The short side is opposite the 30-degree angle. If this is 60, then this is the 30, and so that is the opposite side of 30. We have the short side, which means the rest is very simple. X is the hypotenuse, the longest side, so x is literally 2 times that. 2 times the short side length. And so that times that is just simply the square root of 5. And y is the square root of 3 times the short side. So using radical rules and stuff like that, this is just a fraction times a fraction, so you multiply the numerators, and the square root of 3 times the square root of 5, we can merge back into one square root of 15, and the bottom is simply 2. And there's your answers for that one. A lot of times you'll see these kind of pictures and stuff on standardized tests that say find the area of the shaded region, and it's really a question about spectral right triangles. So we can look at this thing right here, and this is 2 times the square root of 2. And so I can use this right here and recognize that this is a, usually they tell you it's a square. I'm telling you it's a square. And you can find the area of the big square and subtract the area of the small square to get the shaded region. Okay. You also have 4 of these little triangles. So you can recognize that they're all symmetric. So you can just simply take this piece and that piece together and make a square. That one and that one make a square. If this is x, then this is x. So there's a lot of ways to look at this problem. But if I want to find out what x is, then I can recognize that I have a 45, 45, 90. And if this is 2 times the square root of 2, then to get back from the hypotenuse back over here, I simply need to divide by the square root of 2. So that tells me that x is 2 times the square root of 2 divided by the square root of 2. So x is just 2. Okay? And so then I can use that to find the area of the shaded region. And you can find the area of each triangle, times it by 4. Like I said, there's a lot of different things you can do. And so if I want to find the area of this triangle, it's 1/2 the base times the height. So it's x squared over 2, and I have 4 of those. So the area of the shaded region is 4 of those. And so then I have 2x squared. So, like I said, a lot of things you can do. That was just one option available to you. You're going to be building the unit circle. And as this down here is kind of showing you the relationship between central angles and special right triangles. So find the coordinates, find the name of that point right there. If I know that that angle is 30 degrees, I can do so because I need to know what the x is and the y is. But I know the hypotenuse. The unit circle means the radius is 1. So I know the hypotenuse is 1, so I can use my special right triangle rules, and I can figure out what x and y are. So in this triangle right here, y is the short side, and y, the short side is half of the hypotenuse. So that means y is going to be 1/2. So remember, in the 30, 60, 90, you always go to the short side first, and then from there I can go and find the other side. So since the short side to the middle side is u times by the square root of 3, x must be the square root of 3 times 1/2, or the square root of 3 over 2. You can do the 60 degree over here the same kind of way. The only thing that's different over here is that the 30 degrees is now opposite the x. So that means now x, is the 1/2, and y would be the square root of 3 over 2. So that's what happens in here. These things just change places. And this one over here is the 45, 45, 90. If this is the hypotenuse, then the x and the y will be the same value. And from the hypotenuse to the side is you divide by the square root of 2. So that means x is going to be 1 divided by the square root of 2. And you can think of it that way. But if I rationalize it, then I get the square root of 2 over 2. And that's usually how it's displayed. So it means both x and y are the exact same number, the square root of 2 over 2. So you're going to be asked to probably start building your unit circle with this concept. So that's where those numbers come from.